Hello, I'm Bob Adams with Tribis Engineering, and I want to thank you for coming here. Today I'm going to talk to you about automated test processing and how that relates to the scientific community as well as to the manufacturing side of things. Like most everybody here, I started out, I always wanted to be a tribologist. I wanted the glamour of the job, and you can see I had a better tan back then. I didn't really start out that way. I started out as an engineer, and my path into tribology was a little bit different. I was an automation guy. I was designing special machinery, process machinery, assembly machinery, material handling, all automated systems. And what I ended up doing was designing things so that they wouldn't need maintenance, because number one, they wouldn't get maintenance even if I required it. Number two, if they got maintenance, it wouldn't be correct maintenance. And that got me into plain bearings, lubrication-free bearing materials. And hence I became a tribologist. Sometimes, though, in testing things and using materials, you need to know how the material is going to behave in your application. What you want to find out about the material isn't always covered by a standard test. The ASTM has a lot of standardized tests, and they're very good for comparing one material to another, but they don't necessarily tell you what you want to know about the materials. What I want to say is that historically speaking, the automation side of things, the machine building people, and the research and testing people have been very different fields of engineering, or in very different fields of science. And what an engineer or an automation system is really interested in is how do I make something? How do I control my process? How do I do something that makes somebody else money? Where on the scientific testing, what we're really concerned with is want to learn something. How do I learn something? But there's a lot of commonality between the two. And I want to talk about that. The scientific side of testing to find out something, and the automation side of knowing what it is you do. Start out, when we want to test something, we need to clearly define the test. We have to know what it is we want to know. And the same thing goes for an automation system. We have to clearly know what it is we want to make. We have to control the variables on the science side, whether that's our pressure, our velocity, our temperature, our radiation, whatever the variables are in our test, we need to control them accurately and precisely. And the same thing goes in the automation side of things. We need to control what we put into a product, how we make it. It's always got to be accurately controlled. We need to get rid of operator variability. If you have somebody set up a test, and the next time he sets up the test, he may do it a little differently, or if somebody else comes in and sets up a test, he does it a little differently. It causes problems. Likewise, in the machinery world, we have something called gauge R&R, and that's where we are looking at how we measure things, our reliability and repeatability. How can we be sure that every time we measure it, it gets measured the same? It gets measured within some repeatable degree that's acceptable, that it's done correctly every time. We need accurate measurements on the scientific side. It doesn't do us any good if we can't measure what it is we're trying to measure, and measure it accurately enough to make some difference. We need to control that process so that what goes into it is always the same, and we can measure that it's what we're getting out of it is the same. We need repeatable results, both cases, product or results, the test. We've always got to make the same thing. We need to record that data in both cases. What is it we learned? What is it we made? We need to be able to analyze the data to determine our overall quality. We need to validate that data. Was that test any good? Did it mean something? Did we actually learn what we intended to learn? And on the other side is our product right? Is it what we intended to make in the first place? Like I said, with the analysis of the results, and then also to look at production trends. Very similar processes. There's an analog for each on both sides of this. So what I want to do is use a case study here of a system we built for a customer that wanted to do wear testing of plain bearing materials as part of their development process of developing new materials. They wanted to be able to get a broad spectrum of the properties of a new material and then compare that with others they developed, and so they needed a very wide range of data out of this. So the goal was to develop a wear map for plane bearing materials. Our variables would be the contact pressure and the sliding velocity. The problem is it takes a long time. The typical test can take anywhere from, using ASTM tests, can take anywhere from 8 hours to days. I've seen even some systems running for months just to get a single pressure velocity wear rate. In order to get a map of how material is going to be, we might need 25 or even 100 permutations, various pressures and velocities. You put them together and you can develop then a 3D surface map based off how something wears. If each operation requires operator interaction, it takes a lot of time. You maybe get one a day if you're lucky, and to do 100, it certainly becomes a career move for somebody for one material. So what we really needed to do was set a set of goals for this test system that we were going to make. One was we needed a high resolution method of measuring wear. Instead of measuring wear at 1/10 of a millimeter range, we needed to measure it at the 100th of a micron range. 10 nanometers is where we were targeting, just so that we could cut down the amount of time required to actually measure wear. We needed to do this measurement real time, in situ, so that we would actually watch the wear as it happens. Let the automation system then determine when enough wear had gone by that we could accurately say that the data was good. We could work with it, proceed on to the next permutation. We needed to precisely control the variables. In this case, it's contact pressure and sliding velocity. And we needed automatic data collection and graphing, because for one person to generate all this would be just a terrible job. So it needed to be a fully automated system with no operator involvement required, where the operator would come in, he'd set the materials in place, he would tell it what kind of a test to run, and he'd hit the go button and walk away until it's done. So in order to do that, we needed a high-resolution measurement system. So the thought was to bounce a laser off of the back of the sample. And as the material wore, we could pick up the variance in the material wear with a sensor. And this is what we did. We mounted our samples, and I can point here, this is a graphic of what we did. Our sample holder would be here, our materials down here. We bounce a laser off the back, and that laser then measures how fast this sample holder moves down relative to the wear surface, this counterface surface, which in this case is a spinning disc. We used a secondary laser on here also to give us a differential measurement. So the first thing is we end up with a 10 nanometer resolution on the laser. Second, the dual laser system then cancels out variation. As the system runs, things can heat up and cool down the whole system, and what we do by doing the differential is we take out the thermal variation in the whole system. The only thing we have to be concerned about is the swell of the sample itself. Also system runout, because I don't care how good a machinist you are, in a manufacturing system you're not going to make something that's going to be steady to 10 nanometers. It isn't going to happen. So we have a dual system that cancels all of this out. The second thing we needed to do was to control our load, and this was a little trickier because we needed to develop something that didn't already exist for this. Normal air, we're going to decide to control it with an air cylinder, and normal air cylinders, you can get them one of two ways. Very tight, no leakage, and very loose, lots of leakage, low friction. So you can either have low friction and air leaks all over the place, or you can have high friction without much leakage. So we developed a rolling diaphragm cylinder that has zero leakage and very near zero, and for all intents and purposes of our testing, zero friction. With a servo system, we can accurately set and control the speed. What's nice about it is a servo system actually operates under a velocity profile. It's trying to maintain where it is relative to how fast we've told it to go. So if we're telling it to go 4 meters a second, after 100 seconds, it expects to be 400 meters from where it started. And it's going to be at that distance relative within some small variation that we allow. In this case, it's just a few millimeters. So it doesn't matter how long we run, our average speed is going to be very accurate. As a matter of fact, the longer we run, the more accurate our average speed becomes. It also has automatic compensation for the load. So as the load changes, it increases motor current, the torque goes up, it maintains the speed regardless of what happens. And as I said, we have a window for accuracy that we define in this thing, so that it must be at any point in time within a certain range of accuracy, or it lets us know that it cannot maintain that. The computer system then can do something about it. So we create a control plan for the whole system. And I'm going to start out at the bottom of this with the RDTS, which is our Rapid Dynamic Tribotest system. That is the hardware side of the system that this runs. This is think of it as a mechanical function library. It does what we tell it to do. We have a programmable logic controller, or PLC, which then controls the operations of the mechanical system. It applies the load at the air cylinder. It tells the servo system how fast to go, and the servo system drives the motor, and it monitors that it is all in fact doing itself. On the outside of this, we have a workstation which analyzes the data that the PLC is collecting from the system and streaming to it. It watches what's going on and it determines when tests are sufficient. It tells the PLC which test to do next, to start, when to stop, and how to move on. And the final thing is we have a SQL server built into the thing that continuously collects the data as it's going along, so that a researcher then can review the data, analyze the data, agree with what the system has done, invalidate it, but also importantly, no data is ever lost. It is not possible for an operator to delete data. That's certainly a supervisory function. It isn't going to happen. So data is always there. The original data is never lost. You can come in, you can say, I disagree with the start and stop points, and he can set new ones, but the original computer choice is never lost. And this is a picture of one we built for, it's currently sitting in DuPont's testing labs. Now I want to show you a little bit what it puts out. First off, I've got a couple of graphs here that I want to talk about. These are individual test graphs. This first one here is a test of the material running at a relatively slow speed, 200 millimeters a second, and contact pressure low, 1 megapascal. This next graph here is a higher speed and a higher pressure, 1600 millimeters a second and 8 megapascal. You can see what I've got is two similar looking graphs. There's some noise on one. The numbers at the top tell us the wear rate in nanometers per meter, and the correlation is how good that data is relative to the linear fit slope. This screenshot right here is a shot of actually 78 tests that were run in this sequence. After the 78th test, or at the material failed, and so the system automatically stopped itself. But each one of these represents one of these graphs, an individual test that's been run. And then when it's done, we put all of that together and we get some maps out of this thing. This first map is a wear map. Remember I told you that slope on the top of the previous one was in nanometers per meter? Well, that's what my vertical axis here is, my wear rate in nanometers per meter of sliding distance. We can also use the old Archard wear, which is based off of sliding velocity, but it has less to do with a broad spectrum of tests, and we can derive it. But we get a lot of people asking for it because they've used to seeing Archard wear for 40 years. But this one is, each one of these represents, these cross points represents an individual PV test. And this particular one is not the same material I showed you before, but each one of these is one of 100 permutation tests. And by the way, this whole test was done in a 24-hour period instead of one test every day. The second one is a map of the coefficient of friction. And as you notice, it starts out low, then it very quickly jumps up high with pressure, and then as the pressure increases, the coefficient of friction drops back off, and there's very little change in friction relative to speed. And this is one of several characteristic surfaces we have found. And the real holy grail in all this is the heat generation. because so many of the tests we've run into have to do with they fail, they create what's called a PV limit and they fail. And this PV limit really is appealing to scientists and engineers because pressure times velocity is energy. And it would make sense that we'd have an energy rate that our material couldn't handle, and so therefore it'd be a great material property. Well, we found out, though, that that's not the case. Our limit's really a thermal limit, and the heat generation determines how hot it gets at that surface. The better we can dissipate heat, the higher the rate the system can run at. And we have done some tests with materials that are operating at about 200 times the pressure velocity, the PV rate, that they have limited in their catalogs as their limiting factor. And the difference is because they were done on a different system that overheated by that point in time. So given the heat generation and the geometry of the system, we can then do some finite element thermal analysis and determine whether an application is good. That's really the holy grail of this whole thing, and not a PV limit number that we were used to seeing. There's one, we got to define a process. When we're going to make a new automation test system, we define the problem. What is it we want to measure? What variables are we going to control? And what do we want to get out of this? And then we have to determine what are the methods. How are we going to measure the things we want to measure? In this case, we used dual differential lasers. And the other one is how are you going to control and isolate your variables so that they're not affected by other things. And the last thing you need to do is define a control plan. How do you want to put this whole thing together? How are you going to, is it going to operate? How is we going to collect the data? What is the whole interface for the system? It is the plan that allows you to put the whole system together. Then you get to the point where you're actually able to design and build the test system. What are the goals? What could you do? We could, in this case, we were interested in dry sliding. Maybe you have an application-based test you want to run. You have something that you do over and over again, and you want to have a way of quickly validating that test. So you build a test specifically for that. Maybe you're a materials developer, and you want to test lots of variations on how we make our material, what our recipes are that we put this together. You build a system specific to measure what it is you're trying to do. Receiving inspection, how do you know that the material you're getting in is good? And sometimes you can't tell by running a test on it, and that test may take too long otherwise. Maybe you're testing seals. Seals are an interesting problem. They got to keep oil in and they got to keep dirt out. And they don't have a lot of contact pressure unless they're a pressurized seal. What is it you want to measure? How do you want to test this? What about your lubricants? How do you want to measure your lubricants, their capabilities and what they can do for you? Rolling bearings. There's a lot of applications you can develop a system for that test specifically what it is that you want to learn. And that is what I said earlier on. A lot of times standardized tests don't tell you what it is you really want to know. And that's what our job is. We do tribological testing of materials, do consulting on the testing for you. Help you develop test methods and for your processes that fit your needs. And if you need it completely, we'll design and build a complete test system. And I want to thank you for joining me here today.